All right, we're gonna go right into this guy. I don't think we'll have time to go through all of it, but that's okay. I'm gonna go through it pretty quickly. So statistical testing, yes. So basically our statistical tests are basically saying, when we do a statistical test, we're trying to say, hey, is this thing because of just random chance, or is it because of something different? So usually you can think of it like, let's say a health medical application. You can say, okay, if I give someone a placebo, which is supposed to do nothing, versus give someone medicine, does the medicine actually do something, or was just random chance that would have happened by itself? Okay. So one thing we can do is the z-statistic, and z-tests, z-statistic, z-tests. This is a classical hypothesis test what you use with normal curves. And basically all you have to do is say, okay, we have our sample mean, x bar, that's what we have represented here, our population mean, right? And our population mean, I should say, it should be a population mean, but mu here, this mean, is representative of the control. So the control could be the population, but it could also be another subset of people. So imagine like if you want to compare men versus women or something like that, you could use, you know, X being like, you know, men, and then mu being kind of like your control of women or something like that. Okay. Your Z statistic basically is telling you how many standard deviations are you from this mu, right? And that's what this basically is representing. You can think of your Z score, which is literally the Z statistic, is saying how likely is a value this far from the mean to be part of the same group. Okay, so the larger your Z statistic, the less likely it's actually part of that group. So you can kind of imagine like most people are surrounded in this normal curve right around here. A Z statistic with a very large value will be over here or over here, basically meaning that it's a very rare occurrence where you'd actually get that sample mean over there. So that's the idea of like the Z statistic. Okay. Hypothesis testing. When we actually do a hypothesis test, we have two parts to it. And I will say for the record, whenever you do a hypothesis test, you should always start with writing out your null hypothesis, writing out your alternative hypothesis, like literally write it down. This will save you so much. And also it makes you less likely prone for something called p-hacking and other things, which we'll probably talk about next time. But the first part is the null hypothesis, which is your H0, right? And basically assumes nothing new, no effect, your placebo, whatever. It's kind of like your baseline, that's your control. Your alternative hypothesis, HA, is saying there it was an effect. There is some difference between the control group. So note that your control, your null hypothesis, can be a different group. For example, like men versus women. Your alternative hypothesis basically saying, like, well, what if, you know, there is a difference between men and women, or whatever it is, right? Let's say men and women's weight, right? Is there an actual difference between the two? Your goal with hypothesizing is to attempt to reject the null hypothesis. I'm going to really bring this into you guys, is reject the null hypothesis, not accepting null hypothesis, not accepting the alternative hypothesis. It's to reject the null hypothesis, and that's all you can really say. The way I kind of phrase this is that you never know if you always get, you never know everything. So you can only assume, like, if you can you can disprove gravity if you can find an example that doesn't work. Like, gravity should do this thing, but it doesn't work. That would be disproving gravity. You cannot prove gravity because you would have to assume that you tried everything in the whole entire universe and know every interaction and know that for sure. It's just impossible. So really what we're trying to do, we can easily disprove something. We can never prove something. And that's what this reject is saying. It's like we're disproving the null hypothesis, which means there was no effect. Does that make sense to people? Cool. All right, I realize it's a little bit over time. I think if you guys are okay with it, give me a thumbs up if you guys go like maybe a few more minutes. Okay, I see most people. Okay, I see some nods too. Okay, maybe I'll go for 5 more minutes just so we can get through this part. So that is the main thing I want to drill in, reject the null hypothesis. That is your goal, okay? So note that hypotheses are based around the normal curve. So we have types of different hypothesis tests. So this is where we have like right tail, left tail, these are one-tailed tests. And then in the question earlier today, we talked about two-tailed tests. Basically, you can say it's just different from each other. So your null hypothesis basically says mu is equal, like population 1 is equal to population 2. There's not a difference. Your alternative hypothesis will look something like mu is greater than this value, or this value, let's say mu1 is greater than mu2. So this is like 2 different populations. This is how you would write out your alternative hypothesis. Note that some people will sometimes switch from one-tailed tests to two-tailed tests. You should not do this. really think about saying, am I looking for a difference or am I looking for a strict difference? In general, I will recommend don't use two-tailed tests unless you feel like it's very necessary. In general, you should be thinking about, is there a strict difference? For example, if I said, is there a difference between weights of men and women? You wouldn't want to say something like the weights of men are different, are greater than weights of female. And so you could use that kind of comparison. You could say they're different from each other, but that's a little less conservative. You're more likely to be able to prove this correct and not know which direction it is. So in general, it's better to have this in mind. It's more conservative, but it means if you can reject the null hypothesis here, then you will reject the null hypothesis here. If you reject the null hypothesis here, it might not be sufficient enough to actually do this part, which I know is kind of confusing, but this means that basically you're saying for sure, like, I really know it's going to be greater or less than. Okay, makes sense. Cool. All right. All right. So this is where I'll bring up p-values, and I think this is where we'll kind of end up finishing a little bit. P-values are super confusing. Basically, you can think of your p-value as the probability of you being able to reject your null hypothesis by random chance. So I think this is where I'm actually going to not go into full details. I just sent on the Zoom chat this article that I linked over here that explains p-values with puppies, which is just great. It actually does a really great job, but basically your p-value is describing how weird something is. Like if you have a low p-value, it means really weird situations would have had to happen. Can they technically happen? Yeah, they could technically happen, but it probably means something else. And that's where you fail to reject your null hypothesis. If you don't like the article too, I think there's even a link to the video. I think they made a video. I'm sure there's a link in here somewhere. If not, I'll show you guys next time. But this person who did this article on p-values, I think does a really great job of explaining it. And they actually wrote a little video too. Oh yeah, there's some video somewhere in here. Okay, so homework for you guys. Watch that video, read this article. Okay. I'll briefly just say there's something called p-hacking. I'm not going to go into full details since we're a little over time, but basically there's ways to adjust your p-value or retest over and over again that make it more likely you to find, oh, I rejected my null hypothesis. This is, again, XKCD is great at doing this, but basically one is basically saying, you can adjust, say, what level do I reject the null hypothesis? So if your p-level is usually it's 0.5, that's your alpha, your significant value, your significant level. You can adjust this. Say, well, what if I reject it if it's like 0.1? Like that's all right. Like that's kind of p-hacking. You can kind of adjust things. So that's one thing you can do. So we'll talk a little bit more of this next time. And then the other one is that basically this is a really great one, I think. If you test over and over and over again, or test many different categories that don't actually matter, just by random chance, you might find something that is significant. And so here you see, like, they're testing for like if jelly beans cause acne, and they find out a p-value greater than 0.05, which means they fail to reject the null hypothesis. They need a p-value less than 0.05 for the results. And they say, oh, wait, I think color matters. Now, you guys knowing jelly beans and probably got a good guess. Do you really think jelly beans cause acne? Probably not. But also, would the color really matter? Probably even like less so, right? But what's kind of cool is that they actually show this with 20 different colors. That's why XKCD is so good. And you can read all of this stuff. And there's one particular one, here it is that with green jelly beans, they found a p-value less than 0.05. Well, 0.05 is 5%. 5% of the time you expect to fail to reject the null hypothesis, even though it's like you should have rejected the null. You reject the null hypothesis even though you should have failed to reject it. And so 1 out of 20 times, 20 different slides here, just by random chance, you'd expect to actually reject the null hypothesis, even though it's just pure random chance. And so this happens all the time in p-hacking. And you can see this is the news article. And I will tell you, I will show you guys next time, there is actually a direct example of this that someone had done. They literally said, I'm going to purposely publish this into an article, not an article, but like a scientific journal. And this will basically, people misunderstand this. And because I'm going to basically just test a whole bunch of things. It ended up being about chocolate, and they ended up finding, anyone ever heard this thing where either chocolate or dark chocolate helps you lose weight? Has anyone heard something along those lines? I see Alvera kind of give a nod and something like that. That is the study I'm talking about. They purposely said, I'm just going to do the study that's completely legitimate and people are going to interpret this and actually use this and say it's significant, which technically it was, but what they did, basically they tested a whole bunch of things. So we'll talk about that next time too. I have a good article of the original scientist who did it. Okay. And then at the end, I just have a quick like steps for z-tests. Jeff, another instructor, does a great walkthrough for z-tests. I think he actually looks at NFL, or not NFL, NHL, hockey, and z-tests and significance and stuff. So I strongly recommend watching that. But these are the general kind of steps that you would do to do a z-test. And this will lead us into other tests like t-tests and Welch's t-tests. Okay. Sound pretty good? I know I kind of walked through this relatively quickly, still took me a little bit, but we'll hop on to this again. Next time we'll talk about more statistical tests, more on statistical tests about like how does p-hacking effect size, and then I'll also talk about t-distributions, t-tests, which is still part of section 14, but that will lead us into interpreting from like Welch's t-tests, what's it, power, and all that good stuff. Okay. All right, everyone. Well, I will stop it here. Unless you guys have any quick questions. No, pretty good. All right, everyone. Well, I'll stop the recording here then.